Hi, everyone. My name is Gustavo Araujo. I am a PhD student at Oregon State University. And today I am presenting on the seismic design of mass timber pivoting spines and how we applied it to a three-story building at Oregon State University. I am one of the many researchers involved in this research project. Uh, Previous presentations have mentioned the concept of spines, but let me just briefly go over it. It's basically a portion of the structure that is designed to remain essentially elastic. And the idea is that by doing so, it controls story mechanisms and also helps propagating damage across all stories. Um, in mass timber, but in general in the industry, there are two types of spines that are becoming very common. The one is rocking spines, such as the frame that you see here. This is a frame that uplifts at the base, and the frame basically constitutes the spine in this case, while energy dissipation is provided by some exterior mechanisms, and they typically add a pause tensioning to help recentering, and that way we are also limiting residual displacements. The concept has also been applied to precast concrete walls and mass timber walls, as I'm showing here, where now the spine is, instead of the frame, it's the wall. The other type of a spine that I want to discuss today, and the main subject of my research, is pivoting spines. One example is the one that you see here. And how a pivoting spine differs from a rocking spine is that the rocking spine, it uplifts and also impacts the foundation when it's shaking, while the pivoting spine at the base only has a pin connection that controls the uplift, and there's no impact. There's no that extra damping added in the um, in the system. When it comes to well, I'm highlighting here the spine. When it comes to precast concrete walls and mass timber walls, we can design a pivoting spine if we design a connection that allows the wall to pivot at the base and not impacting the foundation, which could be beneficial because we are limiting then the occurrence of crushing at the base of this spine. Limited research is available right now in pivoting mass timber spines. So at OSU, what we did is that we designed and built a three-story building that employs a mass timber pivoting spine, as you can see here, with VRBs as energy dissipators. If I zoom in, you can see how I have here a gap for pivoting. That way, the wall is really not taking any moment. The moment is taken by the BRBs, and the wall is just transferring shear while rotating freely about this point. It's not shown here, but we're working on the design of this pin connection here so that it truly works as a pivoting spine. The way that we designed this spine was in two steps. The first step, and this is basically the methodology that we're proposing, is the design of the energy dissipation system, in this case, the BRBs. And this follows just regular ASC 7. We use an R equal of 8 for the BRBs, and we size the BRBs to take the overturning moment of the structure. Once we have designed the energy dissipation system, we proceed to design the spine, and we do that in two sub-steps. The first one is a stiffness design. We use a displacement-based design approach using the design displacement response spectrum, and we find what's the maximum period that the spine system should have to limit story drift to 2%. And then we propose an equation that employs the material properties of this and geometrical properties of the spine and the BRBs to determine the period of the structure such that the design can be done very quick without a numerical model. The second step in the design of the spine is the strength requirement. The spines need to remain elastic for the forces delivered by the BRBs. And additionally, it needs to be designed for the near elastic higher mode effects. We do so in this research by employing a second mode elastic force pattern with an R equal of 1, but other methods are available, such as response spectrum analysis. We wanted to keep it simple such that it could be easily implemented in many design methods. We have already built this structure, and as you can see here, and this structure will be ready to test in the upcoming month, where we expect to gain the insight on the behavior. Thank you very much to all of you for listening to this presentation. And now I am open to questions that you may have.
Questions for Gustavo?
So do you think that like the design also like prevents sliding in the foundation between rocking systems? A lot of times you have like sliding also. Rocking,
Do you mind coming here to ask? Sorry. Sorry.
My question is, if you do you know, like in rocking systems that sometimes you have sliding at the base? Does the pivoting system also help with that? It's technically.
It's all up to how you design the base connection. So in this case, it's not something intrinsic to the pivoting system. It could be done also in a rocking system, but if I go back to my my slide here, we prevent sliding using a very stiff shear key here. But this is something that you could also do in a rocking system. Basically, this connection is bolted and it's so stiff that keeps everything in place, and the connection here is designed to be slip critical. But it's not intrinsic to the pivoting spine concept.